Okay, let's talk about factors that affect which fuel is used during exercise. This is chapter 3 of the law of running. And we know that there's some clear factors that will influence when carbohydrate is used or when fats are used for exercise. So let's go through this. So when intensity of exercise increases, carbohydrates become more important for energy production or conversion of chemical energy to mechanical energy. Classic idea, only carbohydrates are used at intensities greater than 95% VO2 max. However, it is possible that intermuscular triglycerides, fats, are used at high intensities as well. And this is some of the shift in the paradigm with the type of substrate used during exercise and using that phrase I've used before of being metabolically flexible, where you can train your body to use different types of fuel, seems to have some weight to it. But the take-home point is carbohydrates are the principal fuel at high intensities. Okay, and so even those people who advocate for a low carb, high fat diet, if you're going to do a high intensity exercise bout, you need carbohydrates. Or if you do a endurance race that includes lots of changes in elevation or lots of changes in speed based on strategy, you need carbohydrates. So higher intensity, more likely you're going to need carbohydrates. All right, so let's go through this a little bit. This is just a classic hand-drawn type of figure that you'll see in the textbook. So on the y-axis is percent total fuel source, and on the x-axis is exercise intensity. And then in the clear bars is fat. And in the shaded region would be glucose or carbohydrates. So at low intensity, mostly fat, this is 100%, and some glucose. Mid-range intensity, about 50-50 fat and glucose, and higher intensity, less fat, more glucose, but still having some glucose. So remember fats are triglycerides or free fat fatty acids. Keep that in mind. Glucose is getting to the muscle via the liver glycogen, but we're talking about muscle glycogen used. So once it goes into the muscle. There's just another way of looking at it, percent energy from fat and carbohydrates on the x-axis and intensity of exercise on on the y-axis, and on intensity of exercise on the x-axis. And we see a less reliance on fat as intensity goes up and a greater reliance on carbohydrate as intensity goes up. Where these two lines cross is an interesting an interesting phenomenon. And what some coaches and athletes are trying to do is shift this point to occur at higher intensities so that you're using fats more so at intensities greater than what's listed here, which would be just below 50% intensity, 50% VO2 max. But if you can move that intensity upwards and use fats, that may be a good thing. Why? Because fats are readily available in the body, and you don't need to replenish them during exercise. All right, but the bottom line is carbohydrates are used as the primary fuel at higher intensities, but trying to figure out where this crossover between relying on carbohydrate or relying on fats versus carbohydrates is an interesting phenomena. It is interesting to see whether or not you can train to push that point further in higher intensities. This is something that's very contemporary and being talked about. So individuals can respond uniquely. We do have to remember that. And this is a weakness or limitation of a lot of the research, is that we have group designs, meaning that we put 10 people together. Well, you're likely to get 10 very different responses to whatever the condition or intervention may be. We have to remember that individuals do respond uniquely, but in general, when we do a group design, we're trying to figure out what's the best guess in terms of how someone's going to respond. Well, we can't lose sight that the individual is important. So let's look at this individual. Noakes says, not all subjects were able to complete a 3-hour bout of exercise after carbo loading without some carbohydrate during exercise. Different people may be fat burners or carbohydrate burners. The question is whether or not you can train to be a fat burner or carbohydrate burner. There's no clear answer on this yet. Other researchers compared metabolism during rest and during exercise and see a lot of variability. I'm going to get to that. So respiratory exchange ratio, we need to understand this. I'm going to show you some data in just a second. Respiratory exchange ratio, you do need to know this equation. It's the ratio of VCO2, the amount of carbon dioxide, the volume of carbon dioxide exhaled, to the VO2, the amount of oxygen consumed. So used as an indication of substrate utilization, and I'll show you why. RER is the equation VCO2 over VO2. A value closer to 1 is an indication that glucose is the primary fuel. Why? Well, here's our chemistry. Carbohydrate, we add in oxygen, 6 units of oxygen, and we yield 6 units of carbon dioxide and some water, 6 units of water. So RER is the ratio of carbon dioxide exhaled to oxygen inhaled. Okay, 6 to 6, that's an RER of 1. Now, if we use fat as the primary fuel, here's just an example of a fat with that chemical breakdown. We would need 23 units of oxygen, and we yield only 16 units of carbon dioxide, and this is exhaled. And this is just through the aerobic pathway that 16 carbon dioxide units are exhaled, and some water as well. Water is absorbed in the system. So we look at our RER, the amount of carbon dioxide exhaled, 16, over the amount of oxygen consumed, 23 units, that's a 0.7. So a value closer to 0.7 is an indication that fat is the primary fuel. A value in between 0.7 and 1, you're getting a mixture of fuels being used. Now, if we ever go over an RER of 1, that's because we are starting to use the anaerobic system at a greater rate. The anaerobic system will be producing lactic acid. One of the fates of lactic acid is that it can be buffered. The buffering process of lactic acid yields VCO2, or yields carbon dioxide. That carbon dioxide is then mixed in with this carbon dioxide. We'll get a CO2 that's greater than the oxygen, and therefore our ratio, our RER, will be greater than 1. Okay, so estimation of fuel utilization during exercise, 0.7, 100% fat, 0.85, probably about 50-50 fat and carbohydrate, and a 1 carbohydrate. During steady state exercise, VCO2 and VO2 are reflective of oxygen consumption and CO2 production at the cellular level. That is an assumption that we're making. Okay, here's some RER data that are in your textbook, figure 312. And what's important, and this highlights the issue of variability. Here's respiratory exchange ratio at rest, which it's a very low intensity. You would think at rest, people would be using fats as the primary fuel. Here's the number of subjects on the y-axis. So at rest, RER was 0.71, and there are 2 subjects with that RER. There are 3 subjects with this RER, 0.73, 4 subjects, 8 subjects, etc. So these subjects are using fat as a primary fuel at rest. Look at this, 0.92. Here's a subject who had a resting RER of 0.94. That's indicating this subject is using primarily carbohydrates as a fuel at rest. That's really interesting. This highlights the point that RER is highly variable between people. This is the same information just during exercise. So here, this is number of subjects on the y-axis, respiratory exchange ratio on the x-axis. This is the resting data right here. That's these data up here. This is the description of how many subjects had an RER of different values at 25% exercise intensity. So there are 3 subjects with an RER of 0.77, and it looks like 2 subjects with an RER of 0.91. These subjects are quite different than these subjects. This dashed line here is for exercising at 50% and then 75%. And look at this, 75%, we had some subjects with an RER greater than 1.0. Looks like about 2 or 3 subjects at 1.04. That's indicating that they are using a large amount of anaerobic conversion of chemical energy to mechanical energy, because the VCO2 is greater than the VO2. And the VCO2 is greater than VO2 because lactate's being produced, and lactate's being buffered as one of the fates of lactate, and therefore VCO2 will be greater than VO2. The point of this graph is lots of variability. If I'm this subject, I may need to train or eat a particular way, but if I'm this subject, I may need to train or eat a different way. So we can't lose sight that individuals respond differently than the group. Okay, fat, carbohydrate, just highlighting that. All right, variability factors that influence variability in usage of fuel include muscle glycogen levels, training volume, proportion of type 1 fibers, resting blood-free fatty acids, lactate concentrations, percentage of dietary fat intake. These are all things that are different between people that would explain why RER would be different for different folks. Not all athletes are metabolically the same. Not all athletes are metabolically the same. Very important. So we've got to be careful to not apply general rules to everybody. And this is partly why endurance events are so difficult, is because that athlete, that individual, does need to figure out their metabolism. They need to figure out how to take in the right amount of fuel and the right type of fuel during exercise. Our group designs can give us some best guesses, but that's what they are, best guesses. And that helps us narrow down, but we need to do some more work for each individual. Okay, this is just another, hitting this home, but another factor that influences substrate utilization is exercise time. As we go longer in time on the x-axis, it will change which fuel we'll use, percent fat or carbohydrate metabolism. As we go longer, we tend to use fat more as the fuel versus carbohydrate. And this is just coming from data from Costello. 120 minutes of exercise at 65% VO2 max. At the start of exercise, 39% of energy came from fat, but at the end, 67% of energy came from fat. Okay, so the amount of time that we're going will influence which substrate we're going out. And this is a set intensity right here, 65%. And the fuel used during that 120 minutes changed. Duration, as we go longer, duration of exercise, or the intensity of exercise will go lower. As duration increases, fat becomes a more important fuel source. The contribution of muscle glycogen reduces. Liver glycogen, and hence blood glucose, will also become depleted with duration, which again highlights the importance of fat as a fuel or taking in carbohydrate during the course of exercise. So practical point, it is important to take in carbohydrate during exercise to minimize depleting liver glycogen levels as well as muscle glycogen levels. The question becomes, should we be taking in fat? Should we be eating avocado? Should we be eating nuts? Should we be having bacon during an endurance event? Good question, and we'll talk about some of these things. Here's just some data, just sort of hammering this point home. This is VO2 or VCO2 on the y-axis. And this is that graded exercise test that I've indicated before. In green is the VCO2, and in red is the VO2. And you see VCO2, the volume of carbon dioxide exhaled, is lower than VO2 up until this point right here. So that RER is going to be calculated. That's this orange or beige line here. That RER is going to stay under 1. Okay, it's going to stay under 1 up until VCO2 exceeds VO2, and then RER goes above 1. VCO2 is greater than VO2 because we're starting to use the anaerobic system at a greater rate at this point, and producing lactic acid, and that lactic acid is being buffered, and the and the buffering process will produce more CO2 that needs to be exhaled. So we can find that crossover point right here for this athlete, and then we can indicate what resistance level this was, what power it was, and it looks like that was about 320 watts. And so now this athlete should know that at 320 watts, above that, they're going to be producing lots of VCO2. They're going to really be carbohydrate dependent. And below that, they're going to be a mixture of fuels. And maybe you want to train to move that crossover point higher and higher if you're interested in endurance performance. All right, so other factors that influence usage of fuel, fitness does. Classic idea, increased fitness reduces the amount of carbohydrate used during exercise. Alternative explanation is increased fitness leads to increased rates of fat oxidation at low intensities, staving off the need to use carbohydrates. Above 75% VO2 max fitness leads to increased capacity to use blood glucose, and then even spare muscle glycogen. Carbohydrate stores also influences what food is going to be used, what fuel. There's a relationship between pre-exercise muscle glycogen and concentrations and duration of exercise. Experimental limitation, this is the issue I talked about before. If we're using a model to go until exhaustion or to try to cover a particular distance, we may get different results on the influence of duration or influence of exercise on usage of fuel. Is the cause of fatigue reduced muscle glycogen or something else? Increased body temp, shortening cycle fatigue, liver glycogen, or maybe even a placebo. So we talked about this before in the previous section. Pre-exercise muscle glycogen level is important, but we're not exactly sure how. What was last eaten and when is another factor that influences fuel utilization. Low levels of muscle glycogen levels are associated with fatigue. That's the main hypothesis. Attempts have been made to understand how to preserve muscle glycogen. So you can alter your pre-race diet to increase reliance on fat metabolism, but it is not possible to increase fat metabolism by altering the pre-race diet. So you want to be careful about this. Carbohydrate ingested before exercise increases the amount of carbohydrate used during exercise. Refueling during the race is critical to preserving muscle glycogen levels. So what this information that Noakes reviews, what is important is if I have some carbohydrate, if I have a candy bar right before a race, I'm probably going to stimulate the system in a way that more carbohydrate will be used during exercise sooner. All right, so that's what we just need to be careful of. We don't necessarily want to just alter a pre-race diet, although there has been some evidence coming out that contrary to this, that you can eat fat and that might actually stimulate fat metabolism during exercise. So this is still sort of a big question mark. But the key is right now, our understanding is that you don't want to be altering your diet the week before a race. You want to be sustaining whatever diet you had going into a race week. You want to sustain that during the week before the race. Ingesting caffeine. Caffeine appears to have no metabolic value during exercise, but it is a stimulant. It may, possibly because it may lose its ability to mobilize fat when someone has carbo loaded. So we got to be careful that if we take a lot of carbohydrate and caffeine, we may be counteracting each other. The two things may counteract each other. Caffeine does seem to enhance time to exhaustion, so there can be a performance benefit. Benefit could come as much as 4 hours after ingestion. How much coffee, or excuse me, how much caffeine? About 3 milligrams per kilogram. A cup of coffee is about 40 to 100 milligrams. So that's 3 to 6 cups of coffee. So you need to be taking in quite a bit of caffeine. More than 9 milligrams can have negative side effects from increasing urination to shaking, having that edge of having too much caffeine, too much stimulation. What's interesting is the strategy most athletes will take is to take caffeine in the later portions of the race. So even though that may come, there's a delayed effect, you may still get a better benefit of having caffeine at the last half or last quarter of an event versus taking caffeine too soon. Some people complain of GI problems when having too much caffeine. That could be due to a stimulatory effect. So we just have to be careful with this. And it could be the caffeine effect could be due to an influence on the muscle cell in terms of increasing the release of calcium. Question mark, don't know. Big thing, individual tolerance levels with caffeine. Some people are responders and some people are negative responders and some people have no effect. You do need to figure out whether or not caffeine will work. How do you do that? You use it during training. You see how you respond to it. You try different amounts. The fuels that athletes use are usually indicated with the amount of caffeine that's in it. So it's just a lot of experimentation. Ingesting a high carbohydrate meal pre-exercise will increase the amount of carbohydrates. It's a little bit redundant. The classic idea of eating high carbohydrate meal pre-exercise was not recommended because this might increase insulin levels. Insulin is a hormone that controls the uptake of sugars, proteins, and fats. Insulin functions to lower blood glucose levels and allow that blood glucose to go inside muscles. Therefore, one should not exercise with elevated insulin levels. That's going to drop blood glucose levels. That could cause a depletion of liver glycogen levels sooner. But the contemporary viewpoint of this is not all carbohydrates are equal. Carbohydrates with high glycemic index cause a rapid rise in blood glucose concentrations and release of insulin is stimulated. And that insulin is stimulated, that means that more glucose is pulled into the muscle. So you start to see these big fluctuations in blood glucose. But carbs with a low glycemic index cause a smaller, more delayed rise in blood glucose and therefore less insulin response and much more of a level response to what's happening with blood glucose levels. Probably a good idea to have carbs with low versus high glycemic indexes. There's a drink out there that has that uses a starch as the main carbohydrate, and that they advertise that it's a much more slower release of glucose. But if you're exercising for 10 hours, the speed of release is not important. It's probably more important to maintain an even level of glucose levels. This is just showing the difference between high glycemic index and low glycemic index food intake. Here's plasma glucose or blood glucose. This is time, this is rest, this is exercise. This is insulin levels. So as insulin levels go up, blood glucose levels will drop. And so you want to watch, blood glucose levels will go down, which means that the glucose went into the muscle. But now you just need to be careful not to have this oscillation of blood glucose, because you're going to have an oscillation of insulin, and you're going to have an uncontrolled amount of blood glucose, and therefore an uncontrolled amount of glucose going into the muscle. Insulin response is dependent on type of carbohydrate taken in. So the open squares are high glycemic foods, and solid circles were low glycemic index foods. And so the point being that if you take in low glycemic index foods, you have a more steadied response to blood glucose versus high glycemic. This is just a table of glycemic index, and I know there's some debate on where these foods fall within glycemic index. But sugars, syrups, and jams are high glycemic index foods. Legumes, maybe dairy products, are low glycemic foods. So we'll get a spectrum of them. Okay, other factors that influence fuel usage: ingesting a high carbohydrate meal, ingesting food 45 minutes to 4 hours before exercise might enhance performance. There's a lot of variability in how people respond. The way that endurance athletes will take this information is if their race start is at 7 a.m., they'll work backwards and they'll say, okay, that means I need to have breakfast by 3 a.m. So you wake up, have a breakfast, and then maybe you go back to bed, and then you wake up again and have a lighter breakfast. So trying to get some food in you well before your start is probably a good thing. You got to practice this. You do need to make sure your GI system can handle that. The effectiveness of the pre-exercise meal may be dependent on during exercise use of carbs. That is, what you are taking in during the exercise may actually negate any pre-exercise meal benefits. But the whole idea of either of these strategies is you're trying to prevent depletion of liver glycogen. Other foods, other factors affecting fuel usage, nicotinic acid. These are B group vitamins. They inhibit fat mobilization. They are used to treat high blood cholesterol. They're found in meat, wheat, germ, dairy products, and yeast. Inhibits fat mobilization, probably a minimum influence on performance. Fasting before exercise, this is actually something that is talked about quite a bit in the endurance world, whether people should exercise fasted or exercise fed. There's not a clear consensus yet, but I think general recommendations are that you can probably get a better training response if you eat before exercise. But sometimes what people try to do is train their system to exercise fasted because that may happen during a race. But we do want to prevent hypoglycemia, so we want to be careful about that. And so eating is probably a good thing for a training to train at a better level. If you're trying to train in a fasted state, you may run slower, you may bike slower simply because of that. But I keep going back. It sounds like I'm contradicting myself, but this is such an interesting area and lots of information. What some coaches try to do is use that fasted state to try to stimulate use of fats as fuel. So trying to be metabolically flexible. So this seems to be going back and forth, but it's a complicated area. And I'll say again, bottom line, it's important that athletes try these different things out well before race day. Okay, this is important. Taking in fuel during exercise, glucose taken in during endurance exercise does not reduce overall rate of muscle glycogen use, but may reduce the rate in type 1 fiber slow twitch. And during intermittent interval type high intensity exercise, glucose intake may spare muscle glycogen. So if you're going down to the track and you're going to take in, or you're going to do some intervals, take in some glucose. You're going to spare muscle glycogen. Glucose taken in during endurance exercise spares liver glycogen levels, which is important. If you're sparing liver glycogen levels, then you're able to, your liver will still be able to release glycogen into the bloodstream throughout the duration of exercise. So in essence, ingested carbohydrate serves as a substitute for glucose released by the liver. And that could be a good thing, okay? Because then your liver maintains a level of glucose that you can tap into near the end of a race if you're not able to take something in. This is just illustrating some of that. Here's hours of exercise here. On the Y exercise is the percentage contribution to total energy contribution from fat, muscle glycogen, or glucose from liver. And in this graph, the ingested carbohydrate is used to preserve liver glycogen. Okay, so by taking in glucose throughout the endurance exercise, you're able to spare the amount of glucose in the liver. But you see muscle glycogen levels are still going down. Muscle glycogen is still going down. So you're not sparing muscle glycogen use, you're sparing liver glycogen. Oh, this is drinking water. This is taking in carbohydrate during exercise. So this is what happens when water taken in carbohydrate during exercise preserves liver glycogen. Okay, the athlete's regular diet, I've made reference to that. High carbohydrate, long thought to be necessary for optimum endurance performance, but do athletes actually achieve a high carbohydrate diet? And so there's some data in the book where they actually checked athletes, and they actually found that the athletes who thought they were on a high carbohydrate diet were not actually on a high carbohydrate diet. A high fat diet, low carbohydrate fat diet, greater than 50% daily calories come from fat. Now, you may hear the term ketogenic diet. That's where it's extremely low carbohydrate and high fat type of diet. High fat, low carb, high fat can refer to a wide variety of diets that are 50% or more calories from fat. No convincing evidence that performance is enhanced, but this body of literature continues to expand, and there may be some real benefits to people with diabetes to be on a low carb, high fat diet. That's something Dr. Noakes really advocates for. And that's really where he got started on the low carb, high fat diet, was to control diabetes. So if you have diabetes, or if you have a friend who has diabetes or a family member, that may be a situation where looking at a low carb, high fat diet is a good thing. Endurance animals perform better on a high fat diet versus a high carb diet. That's just odd. And so why would humans be different? Is again drawing some questions. And again, Noakes has changed his perspective since writing this textbook. Take home point, a variety of diets can be used that do not negatively influence performance, but this must be a regular diet. Don't change the diet as you head towards an event. All right, so diet influences blood glucose level during exercise. These are just different diets. I'm not sure why I came back to this. I've used this figure before. This is the high carbohydrate diet, the mixed and a low carb diet. The low carb diet being the one that stopped sooner, and the high carb being the one that went further. Those on a high carbohydrate diet used more carbohydrate. Those on a high fat diet reached low blood glucose levels sooner. Okay, so here's low blood glucose levels. High fat diet, they had lower levels of blood glucose sooner than those on either mixed or a high carbohydrate diet. So again, high carbohydrate diet, you're sparing liver glycogen. So as you go longer, the liver can still contribute to blood glucose. So that is sustained. Factors affecting usage of fuel, gender. Women are use more fat than men as a fuel in general during exercise intensity between 65 and 75%, but not always. It may just be a trend, and this is something that needs to be figured out, and something that our research world needs to continue to do is have more females as research subjects. And far too often, the data are based upon men as the subjects, and how men respond may be different than how women respond. And if you are interested, you can look up Dr. Stacy Sims. She's a strong advocate for relying on research for females to help set up female nutrition training programs. During a race, carb loading strategies may be different for men and women, and we have to keep that in mind. The amount of carbohydrate that a female needs may be different than a male. Environmental temperature influences usage of fuel. The rate of muscle glycogen use increases in the heat. Carb ingestion aids performance, but only when heat stress is managed. GI problems increase with carb ingestion in the heat. So we see this circular problem that happens. I experienced this in Ironman Louisville. It was extremely hot. It was in the mid 90s, 90% humidity, core temperature was hot. Trying to eat foods, any food, was actually hard because it was hard for the GI system to try to digest any of that. And so there's a natural reduction, but you do need to, one, slow down in the heat, and then also reduce the carbohydrate intake plan during events that are hot and humid. These are just some data. Substrate utilization in heat and cold environments. These are just some data from Gengen's use of ingested carbohydrate decreased about 10%, but the use of muscle glycogen increased 25% in heat and cool. So just reiterating this, that the type of fuel used in a hot environment is going to be different than the type of fuel used in a cooler environment. Warm up does not slow the rate of muscle glycogen use during exercise. Warm up does not necessarily increase blood flow to muscles or temperature. Warm up does increase blood flow to muscles and temperature of active muscles, but probably not a factor in usage of fuel. It makes sense to increase stores of carbohydrate pre-exercise, and you've heard me say this a few times during this presentation and previous one. And it makes a lot of sense to replenish carbohydrates, take in carbohydrates during exercise. Carbohydrate content of a diet needs to be high. Again, this is debatable. You might want to look closely at the amount of carbohydrate you can tolerate. This is something that an athlete has to figure out, is the number of calories that can be tolerated during exercise, as well as the number of carbohydrates that make up those calories, what the limit is. Because if you exceed that limit, you will have GI problems. You won't be able to digest anything, and then you have a hard time even finishing an event. Almost the same benefit can be achieved by ingesting carbohydrate pre-exercise. So we just want to be smart about the amount of carbohydrate or anything that's taken during an event. So summary part 4, this is a big part, lots of factors that affect usage of fuel and lots of individual variability. I know it's confusing and it sounds like there's conflicting information, and that's because there is conflicting information. We do need to figure out what worked for an athlete. How you figure that out is by lots of practice, lots of training, lots of trying of different fuels, and reading what's on the label of fuels and foods that you are eating. Okay, I hope that's helpful. Thank you.